So the meeting today will be a webinar by Professor Frank Giraldo from the Naval Postgraduate School in Monterey, California. So I'll just start by saying a few words about Frank and some of his background. So Dr. Frank Giraldo is a distinguished professor, chair, and founding member of the Scientific Computing Group of Applied Mathematics at the Naval Postgraduate School. He's also an adjunct professor of applied mathematics at the University of California in Santa Cruz. He holds a Bachelor of Science in Aerospace Engineering from Princeton and a PhD in Aerospace Engineering from University of Virginia. He has a lot of different research interests, including continuous and discontinuous Galerkin methods for solving systems of nonlinear PDEs. He wrote a book on that topic. He also works on time integration methods and some applications to climate and fluid dynamics. And a kind of a fun personal tidbit is that Frank is a very avid surfer. So after this webinar, I think the plan was to hit the waves. So I'll stop there and just hand it over to Frank to start the seminar.
Thank you, Irina, for that introduction. Irina, Pierre, thank you for this invitation. It's a pleasure to be here. So I will talk to you today about time integration strategies for non-hydrostatic atmospheric models. I'm going to use the time integration just to motivate a lot of the work that we're doing in addition to time integration. For example, how to deal with parameterizations or subgrid scale processes. So, oops, let me see. There we go. So I start with some acknowledgements. The talk today will primarily focus on the NUMA model that we've developed in my group. I say it's powered by postdocs. We've had about 13 that have worked on this model and counting, funded primarily by ONR, but we have also funding from DARPA, Air Force, and NSF. And I have a longer list of collaborators that have helped build the model, but for this talk, these are the collaborators that I would like to recognize. One interesting thing about NUMA is that it's the U.S. Navy's Neptune model that goes operations in the end of this year. The dynamics is based on some of the work that we do in NUMA. And if you're interested in more on the model, I have the website here. We also have a close relative of NUMA that we call NUMA-O. The last O stands for ocean, whereas the A in NUMA stands for atmosphere. And this is a model that was funded by DOE in a SciDAC project. And I won't say too much about it, but I will say some things at the very end about what I think could be the use of this kind of technology in the future. So with that, let me motivate the problem that we're trying to solve. So if you look at the very top of this slide, the kinds of scales that we're looking at for weather and climate, you have global circulation models that are on the order of 10 to 100 kilometers, depending on whether you're doing weather or forest climate. And I know climate models are getting closer to the NWP, numerical weather prediction scales, of being below 10 kilometers. But let's just say for the moment that it's on the order of 10 to 100 kilometers. Then you have the cloud scale models, cloud resolving models that are about a 1 kilometer resolution. And then you have the LES, or longevity simulations, that are, say, 100 meters or less. And finally, you have the microphysics or subgrid scale processes that are less than 100 meters, including, for example, moisture, et cetera. And so the standard way of solving these problems is if you're doing, for example, global climate or global weather prediction, the scale that you're resolving is that 10 to 100 kilometer resolution. And then the rest of the processes are parameterized in some way, because we don't have the resolution, and we may not fully understand, what the right governing equations are for those processes, right? And then, of course, there's a way of thinking about it from a multi-scale process simulation, where you resolve, for example, the global circulation. You may resolve the cloud resolving model, and then the LES and microphysics is parameterized. You can also think about this shifting these. Can you guys see my mouse when I move my mouse?
Yeah, all good.
Okay, yes. Perfect. So if you're thinking about, say, for example, limited area modeling, then you can start from this block here and say that this is resolved, perhaps the LES is resolved, but you're not resolving the microphysics, right? So that's kind of the typical thing you can do. So there's two kinds of problems that we're doing. So I already talked about the global circulation being on being between 10 and 100 kilometers. But the idea is that a lot of the models want to get to 1 kilometer global resolution. And when I say global resolution, just for those that are not familiar with weather prediction, this is like the delta X. This is the distance between two grid points, right? And in the vertical, you still have, even at when you have coarse resolutions of like 10 to 100 kilometers, you tend to have finer resolutions in the vertical because that vertical direction is very special. So 100 meters is not uncommon to have that resolution in vertical. So the aspect ratio between the horizontal and vertical it's a very big difference, right? So to my point here about the vertical direction, it's very special because most of the quote unquote physics occurs in this direction. For example, processes like formation of clouds, precipitation of rain, etc. And so I did already mention this LES versus in the cloud resolving model and the GCM, which is the global circulation models. And in this talk, I will show you some results from all of these three regimes. Okay, so let's go to the governing equations of motion. We are interested primarily in terrestrial and also high altitude weather, space weather. So we have the conservation of mass, rho, your density. You have a momentum equation. So you have basically, right, just so we can talk more about the details of this. And then you need a thermodynamic variable, right? So I'm showing you an example of just one of the equations that NUMA carries. NUMA carries 4 different kinds of equations, and I can talk to you more about why we have all those options. But this is the option that we use for space weather, and it's the option that we're retrofitting or has been retrofitted into the Neptune model of the U.S. Navy. There is a 900-page doctoral report from our 3-year project that basically explains like why we came to this conclusion about this equation. But the point is that this equation here, I should say all these 4 equations here, with the equation of state at the bottom here for pressure, this allows you to use, for example, variable composition atmosphere, which you need as you get up to the ionosphere. So this is an equation set that's very powerful for that. Of course, the classical compressible Euler equations with total energy also would satisfy that condition. We also, one of the interesting things about why we're able to carry so many types of equation sets, whether like as you see here, equation 1 is in conservation form, equation 2 and 3 are not, but the classical compressible Euler equations where you use total energy, you can write that easily in conservation form. And so we're able to write all of that within one framework because we use this idea of flux differencing, where we can write any set of equations or nonlinear equations in a flux form that you typically see in balance laws. So what I mean by that is that you can write any of these equations, whether they're in advective form here or conservation form, in this balance law form here, where now this F pound is a special flux and using this idea of flux differencing, we can construct this very easily, which is really nice. It makes for a very simple code because we can play around with all these different kinds of equations and not really change a whole lot except for the flux. Okay, so now what I want to tell you is I want to talk to you about most of the talk here is primarily on how do you discretize or how do you represent the derivative in time using these heavy methods that I'll talk more about later. But before I do that, let me explain to you how we approximate the derivatives in space. So how do you, for example, compute a divergence of a flux? So let's start with that. Okay, so here's your conservation law. Oh, well, here's a balance law, really. And you have to represent your velocity vector somehow. So we choose Cartesian coordinates just because I like Cartesian coordinates. But of course, we want to be able to represent any kind of domain, whether it's on a sphere. So imagine thinking about solving the equation on a sphere or flow in a box. So this is let's say, for example, your global circulation model. Here is your cloud resolving model or your LES model. And we want to be able to support all of these types of domains. So the way you do that is you basically say, I'm going to rewrite this initial balance law in some contravariant form, where here, for example, C and eta represent the horizontal or the manifold that you're on, and zeta represents the vertical to that, right? So in other words, zeta represents in the direction where gravity acts, in direction of gravity, I should say. And so then we can rewrite the equations in this contravariant form, which you'll see why that's very powerful when we talk about time integration. So just to give you an example, now I can come down here and represent the original bounds law into this. So you have a tendency in time. You have a derivative along the zeta direction, which we're going to be able to treat that very specially because that's what I would call the vertical direction where the microphysics acts and gravity acts on. And then you have the horizontal. And the horizontal is just basically the two, what I call manifold components, in this case here, xi and eta. So my point here is that this allows for very straightforward implementation of heavy methods that I'll explain next, regardless of whether the underlying coordinate system is Cartesian, whatever, it really doesn't matter, right? And the idea is to be able to build one code that can do, for example, GCM, CRM, and LES. That's the point here. Okay, now let's talk about how do you actually represent the spatial derivatives. We use element-based Galerkin methods. So the idea in this technology is if you imagine wanting to solve a PDE in this rectangular domain, then we split up that domain into a number of elements or cells, right, that we call omega sub e. And so, for example, this element here, if you think about this element here, there is an associated gamma sub e, which is the boundary of that element, and it has an associated normal vector to each of those faces of that omega sub e. And then we imagine representing our solution in this domain that may have been some skewed rectangle, curvilinear rectangle, doesn't really matter. And then in this new space, it's a perfect square. And then we drop down some interpolation points and integration points. In this case, we use Legendre-Gauss-Lobato points. And then we construct higher order basis functions, right? So we choose these functions. We decide what order we want to approximate a solution with. And so the code is very capable of doing any arbitrary number of degrees of freedom in any of the directions. So here's an example of, for example, what a Lagrange polynomial would look like associated with that point here, right? And for this point here, it would look something like this. And what you notice is that the basis functions are going to be 1 at the associated point and 0 at all other points, but obviously between the points it can vary, right? So here's what we're saying. If you want to represent your solution vector Q of n for some element E, you take a finite dimensional expansion of the basis of some set of basis functions that are functions only in space. And these are the solution variables, functions of time that you're actually looking for. So this is the solution vector, or it's going to be the solution at these points, right? But of course, this representation is valid for any point in your domain. That's the main thing about Galerkin methods. That's very powerful for a variety of reasons. Okay, so now let's go back to our governing equations in continuous form. I now explain to you how we construct the approximation of the solution vector Q of n, and the subscript n here stands for the degree of the polynomial that we're using for that representation, and the superscript e is the element. Then we plug that into for example, the flux and the source, and we grab these approximations and plug them back into the original continuous PDE. And then we end up with a residual that is not going to be 0 because we're using a finite dimensional expansion. So the typical idea here in method-weighted residuals is to take, some piggyback off of least squares, for example, and then you multiply the residual by lower dimensional space, and you recognize that that error is going to be minimized when the basis function and the error are orthogonal. And then we have to make some choices, right? So I've been very general, cavalier about what kinds of spaces we're talking about, but to be more precise, the Q of n that we're looking for has to live in some space. We have to define what that space is. And once we do that, we actually lock in on a specific type of numerical method we're going to be using. So as an example, S could be a continuous Galerkin method, for example, where you're using the basis functions are in H1, and they're also polynomials of degree n. Or you could be a little more general, have a larger space, for example, like in DG, where the basis functions are in L2, but they're also n degree polynomials. And then you make that decision. And there's reasons why you would pick one over the other, but we carry both of these methods in our code base. So at the end, let's go back to the residual form that I showed you before. I'm just showing the actual components of that residual form. There was a derivative with space, with respect to space. This is the divergence of the flux, and then this is the source function that I moved to the right-hand side. So that's the same thing as the one up above here. We do integration by parts, right, to be able to bring in information at the boundaries, which are here. So basically, I'm showing what I did here. I go through, just rewrite this term in a different way, and then I use the divergence theorem here to get this term here. And then at the end here, I show you the final form, which is basically you have the your tendency, your phase integral that gives you information about your neighboring elements and also your boundary conditions at the physical boundary. And then you have these volume integrals. And then I can rewrite this in matrix form, because at the end of the day, we always solve matrix vector problems. So here we have the mass matrix with the tendency of Q. Now I write it as a total derivative because now there's no space, no dependency on space anymore here. This phase integral is this guy here, where I now have to loop through all the faces of my element. So if you think about it in 2D, if you're using quadrilaterals, it's and number of faces is 4. If you're on a hexahedron, the number of faces is 6. And here are our volume integrals in weak form, and then this is the source term. And these are the definitions of these matrices. Here's the mass matrix, which is just the inner product of the two basis functions. And then you have a face mass matrix, which is similar. It's like the basis, the inner product of the basis function at the boundary, and also augmented with a normal vector pointing from the one element to the next element. In other words, from element E to element F. And here's your differentiation matrix. Okay, so finally, here's what we have. I went back to the integral form of the equations, just kind of show you how this works, right? So the way this works is we first evaluate volume integrals. So every element does its own thing, right? So we start with constructing a right-hand side vector that does the volume integrals, which is this weak form differentiation matrix, and also the source. And then you evaluate fluxes, right? And now this is at this point in the algorithm is when you actually need to communicate, for example, across different devices on a computer, whether you're on a CPU or GPU. And so now I have to communicate and know what my neighbors are doing, and it's only nearest neighbor communication. So here's the flux. For CG, these fluxes cancel at the interior of element edges, but not at the boundaries. And then we apply an operation called direct stiffness summation, which is essentially easiest way of representing it is a gather and a scatter, right? That's what it is. Then we multiply by the inverse mass matrix, and then you time step, and that's it. So now I'm going to talk to you next about the time stepping. So I've talked to you about now the spatial discretization, and now let's talk about how do we do this time stepping business. So to do that, this talk is basically, I would say it's the culmination of many years of working on time integration methods for these kinds of problems, right? So you can think of, I can tell you how we got here, but first let me just say that when you're working on atmospheric problems, especially on these global circulation models, if you think about the aspect ratios of the problem, right? You have a radius of the planet that's 6,000 kilometers. So let's say your perimeter is I don't know, 30,000 kilometers, and then you have a vertical that's about 30 kilometers, right? Typically for terrestrial weather. So that's a really big difference in the aspect ratio of the horizontal and vertical. So when you do time integration, if you think about wanting to do implicit time integration, right? If you don't separate out those directions, you'll be spending an enormous amount of time working on your iterative solver like GMRes, just for the simple fact that your horizontal scales are, well, I should say this because the vertical scales are so small, right? So if you're solving a 3D problem, the horizontal is really not feeling like it could be done explicitly, basically, right? For the most part. So that's the idea of trying to decouple the horizontal and vertical. And so these methods known as horizontally explicit, vertically implicit methods have been very popular in these kinds of problems. So what I show you here is how we represent the horizontal operators, whether you're on a sphere or on, in flow in a box, and then the vertical operators here. So that's what this here is what I'm calling HQ, and the direction in zeta is what I'm calling V of Q. So now we can think about treating this V component of the equations implicitly, and the horizontal you can do explicitly, right? So the first approach that we did back in 2013 was we just did the whole thing just fully 3D, right? And the way we did that is we basically constructed an IMEX method, an implicit explicit method, which are called IMEX RS for reference solutions. So the way that works is you basically decompose your solution vector into a known state that has some interesting property that you would like to adhere your model to, for example, hydrostatic balance, geostrophic balance, whatever. And then you have a perturbation from that state, right, which is Q prime. And this worked really well for a lot of problems. But before I tell you the bad news, let me just finish explaining how you actually construct this operator. So then what you do is you go down to you go to your original decompose. Basically, these are your ODEs you want to solve. And then now I construct a linear operator that has the stiffness of the equations, right? And this it's linear because I've linearized about this Q0, which I know, right? I've chosen that state. So then I subtract it from the right-hand side and then add it. And then I say everything in these square brackets are explicit, and this guy here is implicit. So this is my implicit problem, which is linear if I say to you that I'm using a linearization about Q0. So at the end of the day, I take this whole term here that I have in square brackets and with the subscript EX, that's my right-hand side vector that's explicit, and then followed by the right-hand side vector that's implicit. And I try to solve this problem. Okay. And you can use any type of time integration method you want, multi-step methods, multi-stage methods. We tend to use single-step multi-stage methods. We've also played around with multi-step, but I prefer using these Runge-Kutta methods for a variety of reasons. And so in this case here, what we have now is we have, so here's your stage values, so large capital Q superscript I is the stage values at the stage I. And you see that it's actually an implicit problem because there's a QI here, and then this last summation sign here goes from 0 to I. So there's going to be a QI here that isn't, and that creates an implicit problem. Once I solve that, I have to solve an implicit problem at every one of these stages. I goes from, say, 1 to S, number of stages. And then at the end, I do an update solution, and I have my final solution. I have this double butcher tableau that signifies that these are the coefficients for the explicit portion of the scheme, and the next one is the implicit portion of the scheme. So just to rewrite to show you how I get an implicit problem here, I show you here that I move that right-hand side over to the left-hand side, and I show you that I have an identity matrix minus delta T of this operator R of I, and in this case here, this is going to be a matrix, and then times Q of I. So I have to invert this matrix. Okay, so that's great. Good news that it's linear, right? And that it's actually pretty efficient because it's a linear matrix. The bad news is that if the perturbation, the norm or the magnitude, if you will, of this perturbation is large compared to my initial state, then the implicit solution is not guaranteed to remain stable. And a simple way of explaining that is, imagine if you have like the linearization, this that Q0 has no sense of what the velocity fields are. Like say you start your Q0 with basically assume that the velocities are 0, and then the velocities grow, right? For most interesting problems in weather and climate. Well, you're going to have a problem. This system will not remain stable. And that's a problem that we found in our simulations, right? Sorry, let me go back. Did I screw up? Yeah, I did. Here it is. Here, okay, back. So we found that problem when we did these initially with more interesting test cases. If you use kind of very simple benchmarks, things work fine. When you do something more interesting or more challenging, then you see that idea was not going to work. So we went back to the literature. We found a paper on these what we call here, nonlinear heavy GMRes, which is basically you start off with the original idea I showed you before, but But in this case here, this object here, R of I, is never linearized. It's fully nonlinear. So of course, it means you have to use a typical nonlinear root finding problem. And for example, Newton's method. So we take up to second order in delta Q Taylor series, and we recognize that when we get convergence, this function f of qn plus 1 should be 0, and then we rearrange this guy here. And so now we have this Jacobian matrix, which we may or may not build, right? We can choose to build it if we want, but you don't have to build it, right? You can approximate it by using some Fresh-Head derivative, which if I represent this by some approximation that looks like this, f of q of m plus epsilon of delta q divided by epsilon, where epsilon is like machine tolerance, for example, then I can actually build what is known as a Jacobian-free Newton-Krylov method, right? I don't have to build the Jacobian itself. I'm just approximating that Jacobian in some sense. It's really easy because all I have to do is keep plugging in q into the right-hand side function that creates f. So it's almost like if you have an explicit method in time, you can use these methods very easily, right? The only thing you have to do is then you have to minimize this residual using some Krylov subspace method like GMRS, for example. Okay, so here we go. And that method ended up being a little expensive, and I'll tell you more about that in a minute. The other option that our colleagues at the Naval Research Lab that work on the Neptune model, they found the same thing. They said, well, it's going to be too expensive for us. It just wasn't really going to work for us. So what they did is they went back to the original nonlinear heavy method that I showed before, but now they actually build the Jacobian. And once you build that Jacobian, right, you could use GMRS if you wanted to, but you may decide at that point to just solve use a direct solver, right? Because remember, this Jacobian is only along each vertical column of the atmosphere, or that radial component, if you will, on the sphere, right? So the number of points they're not that many. If you think about the grid points along a vertical column, it's maybe around 100, less than 200, as opposed to on the horizontal, we have, millions, right? So it's really not a big problem. So solving this directly using a direct solver is actually very easy, especially if you use banded solvers, because we know what the bandwidth of that system is going to be. So that worked well. And then we thought, well, is there even a better, can we improve that method as well? And so we decided on going back to our original idea, this L-heavy reference solution, but instead of using the reference solution, we linearize about a previous solution, right? So we take a solution at some point that we know, and we linearize the problem, and now we build a Jacobian that is linear, and then we go back to the same machinery we did before with this L-heavy reference solution, and you have basically you solve first the explicit problem, and then you modify the solution by this linear operator. Anyway, so that's what I show you here. We did do a lot of complexity analysis showing what the cost of these methods are, but just to explain to you this plot here in the horizontal axis, the number of points in the vertical direction from a very few to over about, close to 100. And then here, and by the way, this is only the grid points, right? But remember, we have 5 prognostic variables for density, 3 velocities, and a thermodynamic variable. So multiply that by 5. So that's so the size of that problem would be nz times 5 squared, right? So then on the vertical axis you have the dynamic wall clock, basically the wall clock time to solve a problem. And what you see is that n-heavy GMRes scales or grows quadratically with the number of points in z, which we show you here, and in our paper we actually show what these constants are, right? And then the n-heavy LU method it scales linearly with n of z, and then there's this constant C1. L-heavy previous solution also scales linearly, but the constant C2 is smaller than C1, and you can see that there's a big difference here. And remember, I should have said this is a logarithmic plot. So that's very interesting, and it turns out that the solutions between all the problems, whether you use n-heavy GMRes, n-heavy LU, and these L-heavy PS, the solutions at the end look the same, right? So the same stability that you get with the nonlinear methods, you get it with this L-heavy previous solution. So here's a problem that we use to test that idea. And it's just looking at the GCM scale. This is a baroclinic instability that's run. I show you here a 30-day simulation of vorticity, but these simulations have been run for hundreds of days. So I'm only showing you snapshots of 10 days because that's where the literature shows this plot at 10 days. So here's you have longitude and then latitude here from 0 to the North Pole. And endgame is the UK Met Office operational prediction system. And so we use this basically as a benchmark that we want to compare against. And these other simulations here, like SET2NC, SET4NC, SET3NC, are all NUMA simulations that use all these 4 panels here use some form of regularization to maintain stability, for example, hyperdiffusion. And then we show a result with a new model that we have using this entropy stable discontinuous Galerkin methods that are perfectly stable without any viscosity at all. And of course, you do get some noise, but that's to be expected because there's no dissipation except for the Riemann solvers we use in this model. Anyway, I'm very excited about these entropy stable methods. And just to show you a comparison of the heavy using various types of time integrators, we just chose a second order, third order, fourth order, fifth order time integration methods. So here are the N-heavy GMRes, N-heavy LU, and L-heavy, and also time in seconds to do a 10-day simulation. And you see that this L-heavy method is way, way cheaper than all the other ones. And like I said, it has the same stability as the other methods. We don't see it break. So very, very encouraging. Okay, let's see. So to summarize the heavy methods, yeah, I guess the question is, well, sorry, I think I may have skipped something here. Did I skip something? Something is, oh, here we go. Yeah, I did skip something here. So to summarizing heavies, N-heavy GMRS is not a good option for weather prediction models or operational weather prediction models. It turned out to be very expensive. N-heavy LU is a very good alternative. And this L-heavy previous solution is as robust as the N-heavy methods and more efficient. You can think of this method as a Rosenbrock method. I guess the caveat I should add is that so far, all the results have been for idealized test cases, right? So the true test is always when you do real data, for example, terrain, data simulation, et cetera. So this is the next step to see if this really holds for the other kinds of problems that we expect in real weather and climate models. And then the question is, can we do better? And what I mean by that is, well, so N-heavy and L-heavy, these strategies that we talked about today can be extended to fully 3D implicit explicit solvers, right? So we already have this in the works. So here's the idea, right? So imagine that you want to solve a fully implicit 3D problem. So you don't ever have to worry about what time step size is going to blow up your horizontal scales, right? Say if the horizontal velocities get too large, or if your ratio between the horizontal and vertical start getting closer to 1, right? That then you can use fully implicit methods, but they're expensive, right? We have them in our code and we can't use them because they're just too expensive. It requires significant effort in preconditioning. So we can imagine linearizing over previous solution. In other words, we use fully implicit methods, but then we basically rewrite it as a kind of like a linear 3D IMEX problem that we've done before in our 2013 paper, but then we linearize over previous solution, right? And then you have to precondition that problem. So you can precondition that by using the strategy that I've shown you here, for example, the L-heavy method, and then perhaps add on some geometric multigrid. So that's really the idea that we're getting to. And the idea is something like this stacking doll approach, right? So imagine this is your fully implicit 3D solver that needs to be preconditioned by some other solver, which is your linear 3D IMEX problem, linearized by the previous solution. And then you need to precondition that problem. So you precondition it by the L-heavy method. And then eventually you probably need some other precondition, like, for example, geometric multigrid, which we're working on now. And there's other ways to precondition, right? So I won't mention too much about it, but we have a paper that came out in JCP last year on constructing short complements For standard IMEX methods, we did it for the discontinuous Galerkin method for the compressible Euler equations for weather and climate models. And sure complements are great preconditioners, right? Because it's basically constructing a block LU factorization of your monolithic system that then brings that and starts you off from, you start with a hyperbolic set of equations, and it brings it down to something like a Helmholtz operator that's very, very well conditioned, right? So they don't require a whole lot of GM reservations when you have that structure. Okay, so with that in mind, I want to shift my attention to how we are including moist microphysics, right? Because that's the reason why that vertical direction is so special. And I'll talk about primarily the cloud resolving models. So the idea is the following, right? For those that don't know much about this topic. So the grid resolution I've said before, for many models, including GCMs, right, tends to be very coarse. And because of this, we can't really resolve the subgrid scale processes explicitly, right? So what I mean by this is you can think about this in terms of the Lorentz 96 equation. So imagine if you have some large scale process, which is equation 1, which is your capital X, and then you have your small scale process that's your little x here, right? And these two equations are coupled in some sense. So that's what I'm telling you here. X represents some coarse, or what we call large scale process, or LSP. And little x is the fine scale process, or the SSP. And epsilon denotes the time scale separation between the LSP and the SSP. So we do expect to resolve the LSP, but not the SSP. I mean, unless we're using something like LES scale, right? So let's imagine if you're able to do resolutions of capital delta X of 100 meters or less, then you can resolve all of this stuff, right? So option 1 is you use LES and you solve 1 and 2 in lockstep, right? Which can be too expensive, right? And in fact, it is. I'll tell you more about that in a minute. Okay, I'll tell you about them. And then the other option is using parameterizations. I mentioned that in my second slide today. And that the idea there is you replace equation 2, right? Instead of solving some, in this case here, it's an ODE, but think about having PDEs, replacing it by some known function. Little x is now a known function of big X. So that's what we call parameterizations, right? It's a representation of using your LSP variable capital X to represent the subgrid scale. And this is what's currently done in all weather climate models. The problem with that is that this function f is typically non-differentiable, it's non-convergent, zeroth order accurate. I mean, you name it, right? There's a lot of problems with that, but it's what we have. So there's a third option. There's probably other options too. I give you 4 here, but there's other options as well. So the option that I'm going to concentrate on today is this multi-scale modeling framework. So the idea is similar to the LES approach, right? But we drive down the cost by exploiting the timescale separation of the problem. For example, think about using multi-rate time integration methods, non-conforming, adaptive mesh refinement. And there are some choices that you can use that are not so desirable, but unfortunately, it's what we have today. So this is an approach that I'll consider in the next few slides. And then, of course, if this works, right, this option 3 works, you can think of making even it more efficient by, for example, some data-driven version of MMF, right? In other words, replace the small-scale process solver with a neural network representation. We've tried that. We haven't had good success with it, but that's work in progress, and I'm happy to talk to people offline about this, but I won't mention it here anymore. Okay, so what is the multi-scale modeling framework that we're going to pursue here? And I'm trying to get rid of the banner at the top and it's not going away, but that's fine. Okay, so using the multi-scale modeling framework, here's what we do, right? So imagine I said to you, you want to solve a large-scale process model. So this is the course simulation. Think about using, we're thinking about solving a cloud resolving model, for example, flow in a box, right? And so capital Q are your solutions in this entire big domain here. That's going to be coarse. And you have some source functions and you have some coupling function F, right? And then what in standard parameterizations, the coarse scale model then gives this column of information. Every column of the large scale process model is then fed to the parameterization, right? So the parameterization only sees a column of information. It decides what's happening at a scale that the grid scale can't resolve, and then gives you some feedback back, right? So that's the same way the MMFs work. The difference is that instead of using some empirical function f that's parameterized, we basically resolve a LES simulation of that column of information continuously, right? So from time zero to the end of the simulation, there's always constantly some LES model that's running in all these columns, right? And in these small scale process models, this is where the microphysics is working. So we use the microphysics, so conversion from water vapor to condensation, producing clouds, and then clouds saturate to produce rain, etc. Right? So you should be able to resolve cloud formation much better using this idea because you're using the actual PDE, right? There's no real approximation here, except for perhaps the coupling between the forcing that the large scale process model gives to the small scale process model, and then the small scale process model feeds back to the large scale process. And that's the general idea. So here's an example of a squall line simulation, which is a classical moist microphysics experiment, right? And so in the first row here is the actual benchmark running LES scales, or close to LES, right? It's about 200-meter resolution. And here is the MMF model running at a very coarse resolution of 2 kilometers, but of course augmented by these LES scales of 200 meters. And we don't expect to get exactly the same snapshots in time. It's impossible because the resolutions are different, but we get the same general sense of the clouds. So the clouds are in orange here, and the precipitation is in blue throughout the simulation time. Here's a simulation of that. Here we have potential temperature is in the colored contours here. The gray is the clouds, and the blue is the precipitation, just to show you what a simulation of this squall line simulation looks like. And what we have at the bottom here, I'll wait till it finishes here. I'll stop it. And then what we have here is, let me see if I can get that to go away. There, it did go away, good. So this first panel here at the bottom on the left here, this is the standard fine simulation, right? So this is the horizontal distance along here. And then the vertical is time. So it's basically, this is a plot of the speed of the storm, if you will. So that's what this yellow arrow is showing you, what it looks like. If you did just a standard course at 2 kilometers, it looks like this, right? It looks, you get the same speed, but you get some effects that you don't see in the standard fine. And then if you look at the MMF, which basically uses this grid, but augmented at each of those columns by that standard fine simulation, you get a simulation that looks, maybe it doesn't look, I mean, it's kind of, I would say it looks somewhere between these two, between the standard fine and standard coarse, because you have some structures that look like these here, right? But you don't get the structures these structures that you see here. I do see something here though, but for the most part, I would say it's somewhere between these two. Okay, and then that's a snapshot of this, I should say a time history snapshot of this. If you look at the rain accumulation, this is probably more telling. The standard the standard fine is the black line, the standard coarse is the blue line, and the MMF is the magenta line. And you actually see the magenta line sits like more around the, let's see. Where is it? Here's black, right? Okay, so right, so it hovers between the red and blue, and then out here it sticks closer to the red, and it doesn't do this blue thing here. That's the coarser one, right? So again, depending how you look at it, it seems like it's between both of them in some sense. And the kinetic energy, now we use the kinetic energy in the vertical here and time, and it does look like the MMF, which is the magenta again, stays closer to the fine, which is the black line. It doesn't look like the blue line, which is good, right? So this is a result that actually using these kinds of metrics, like looking at rain accumulation and kinetic energy, allowed us to fix some bugs in the code that now we feel we have the right results. Here's the same thing now, but for a 3-dimensional problem called the supercell simulation. And so same thing, you have the color contours are the potential temperature contours. Gray is the clouds, and then blue, you'll see blue is the rain. And if you look at I'll stop it so I can show you these plots down here. Same thing, I show you the benchmark, which is the high resolution model. the standard low resolution model, which is 2.5 kilometers. And then this is the multi-scale model that uses, again, the same resolution as the low resolution model, augmented with some high resolution by injecting like LES high dimensional data into the coarse resolution model. And again, if you look at just snapshot of potential temperature, you see that somehow the cloud formation looks somewhere between the coarse and fine. And the same thing, if you look at surface precipitation as a function of X and Y in time, it's kind of in between, right? So it's not as wide as you see in the very coarse simulations, but not as fine or not as thin, I should say, as you see in the very fine simulations. So, so that's very, very encouraging. I want to turn next to why we care about this, right? And the reason is we're trying to work on these tropical cyclone rapid intensification problems. So rapid intensification, define it simply, is when the maximum wind velocities exceed about 30, well, it's really 30 knots, but let's say 30 miles per hour within the first 24 hours. And this is very important to understand extreme weather. Here's a plot, for example, from one of our papers showing the National Hurricane Center's model in red, right? And our model in green. And we can see that so just to explain to you what this plot is, I should explain that. The time is on the horizontal axis from 0 to 6 hours. And in the vertical, it's the basically the maximum velocities, right? And so all models underpredict this rapid intensification, right? Including the one from the National Hurricane Center. And although I'm not claiming that our model is correct, it certainly gives us a larger maximum velocity in what you would expect in a rapid intensification for a hurricane. And we explain why this happens, right? And that's what this paper talks about. It explains why we see these differences between the models, and it has to do with the accuracy of your gradients of pressure in the vertical direction, right? Very important. So to properly capture these rapid intensifications requires LES models, right? So we need resolutions of 100 meters. But these simulations are very expensive, right? You can't do it on a regular basis, which means you can't really do science. So just to give you an example, the simulation that we did in our paper below, this should be 9 here. This should be reference 9, not 10. Were run using 2-kilometer resolution, and that was 80 million degrees of freedom. And that simulation cost about 1 simulation hour. To do 1 simulation hour per wall clock hour, right? We needed about 5,000 of AMD epic cores. So to do a real LES version of this problem would require a problem that's like, very expensive, right? So something like on the order of 10 to the 4 more expensive, because you require more degrees of freedom, the times it gets smaller, et cetera. So the simulation I show below uses about 10 million degrees of freedom. This is courtesy of Steve Guimond at Hampton University, who used our model to do these excellent simulations of these, hurricane eye walls. So what we see is that to make such simulations possible on a regular basis to do science requires leveraging a bunch of things, right? Like multi-scale modeling framework that we talked about here today, the time integration method that I talked about, perhaps including dynamic adaptive mesh refinement, which we do have in our codes, and we're doing experiments to see if we can bring down the costs, and of course, preconditioning strategies. And HPC, of course, is always important, right? So here's a simulation that Steve provided to us. So this is a hurricane simulation of Hurricane Guillermo using like real airborne radar data. So this is, forcing with real data, et cetera. And this is an XY plot at the height of Z equals 5 kilometers, right? So think about like a 3D column and you slice it at some horizontal height of Z equals 5 kilometers. And you can see the structures of the horizontal wind speed. You see these beautiful, beautiful structures. But this simulation is at 60 meters. And it, we required something like 9,000 AMD epic cores to run on, right? So, not everybody has access to this kind of hardware. So it'd be nice to be able to do something like this with far fewer degrees of freedom, and that we can do on a more regular basis to do science. Okay. And with that, I'm almost out of time. I have about 2 minutes according to my watch. So just kind of walk you through some thoughts, right? current work, what did I talk about today? We described some heavy time integration strategies that make good candidates for use in operational weather and climate models. And I mentioned how to further improve on these by extending them to all three directions, right? So I was thinking about, this stacking doll approach that I'm really excited about, because I think what I show you today is just the starting point. It's like how I envision this work is these are preconditioners that will be able to get us to better time integration strategies. I didn't say much about the spatial discretization, but these element-based Galerkin methods are very elegant, right? The idea of thinking about constructing or using optimal basis functions for the geometry you're solving and the differential operators, and then constructing piecewise solutions within elements and being able to achieve high order accuracy even on unstructured grids allows us to do a lot of cool things in very different areas of geophysical fluid dynamics. Especially for since this is a mathematics of planet Earth, thinking about what kinds of things you could do to solve, Earth problems, right? So on that note, future work, I see that even though these element-based Galerkin methods have been very useful for these weather and climate models, I also see them as being perhaps more optimal for ocean, right? Because there's a greater need for unstructuredness in the oceans to resolve coastlines. I also think these entropy stable methods could play a major role in the construction of provably stable methods, even with complex bathymetry, right? Because in the atmosphere, terrain, it doesn't really play. I mean, it plays a role, of course, but it's not as dominant as it would be, for example, in the ocean, right? So the idea of having entropy stable DG, right, that you can prove that it should never break, should never blow up, and then constructing a fully implicit time integration, should give you bulletproof stability for any problem, right? So this excites me, and I just show you some examples of work that we were thinking about to motivate the use of these methods for ocean. Here's just this is some glacier in Greenland, for example, that we had some ideas on. And on the right here, I show you a tsunami simulation done by our colleagues in Switzerland with our codes using this, dynamic AMR, like what you can do with that. I know this is just a tsunami problem, but I just show it to you here because, it's the idea that you can use these methods to resolve coastlines very easily, and you can perhaps use static refinement in areas that you think are important. I think sky is the limit. So with that, I'm going to stop and thank you for your attention.
Yeah, thank you very much, Frank. Great presentation. So we have time for some questions. Any question? Okay, so okay, Rodrigo. Oh, maybe. Yeah, go ahead, Rodrigo.
Hello, can you hear me?
Yes.
Thank you. So I'm just curious about in ocean models, you're probably familiar with the work of Robert Higdon and others, and there's a need to split the time stepping into a fast and a slower time stepping scheme. So I'm just curious if you have any thoughts on that and how that ties into your work.
Yes, no, that's a great question, Rodrigo. So I have my former postdoc who is the person that made this nice little figure down here at the bottom. Mikhail Kopera is now a professor, associate professor at Boise State University, and his student Yao Gahanzo has worked with Bob Higdon on this splitting. So they took a version of what we call NUMO in my group, and they created a whole new model using just standard. They just did like a two-layer, I guess, shallow water model where they used discontinuous Galerkin methods, and they used the same time splitting that Bob Higdon had proposed, and that seems to work pretty nicely. I still think we can make those time splitting methods a little faster, because the way I envision like split explicit methods, right, is a kind of the general family of time integration methods that split explicit falls under is what I call multi-rate, right? So we have a lot of experience in multi-rate methods, and multi-rate just means that you can construct different time integration methods for different processes. For example, a fast process has perhaps a time step that's smaller, a slow process at a time step that's bigger, but somehow you can write those methods in a way that you can prove formal accuracy of the method you want to shoot for, right? And so that's a topic that one of my PhD students defended it back in 2021, and we have a paper being written on that, on how to show you how to do that for not just for explicit methods, but also for implicit methods as well. But yeah, so I think this is something that I'm very excited to try to look into, to see how we can basically rewrite some of those split methods that they use in the ocean, and using something that is kind of more a general family. But that would work fine with DG methods for sure, and it has been working.
Thank you. I mean, the whole talk and your answer right now, this is all very exciting. And
thank you, Rodrigo. I appreciate it.
And if we couple that with Bob's work on this continuous molecular method, solving a long-standing problem in ocean modeling, which is the pressure gradient computation is problematic, and apparently it might be exactly zero. The error might be exactly zero when used at this continuous molecular method. So combining all of that, I hope there's a way to actually create ocean models that would be much better than what we have right now. This is great. Thank you for your presentation.
I really, I'm looking forward to, explore this area, right? And that's something that I'd be interested in, any collaborations along these lines. I'm not an ocean modeler. I wouldn't even call myself an atmospheric modeler, right? I just, I need to understand the PDEs, but I need someone to understand the physics, right? So thank you.
Yeah, thank you.
Thank you, Rodrigo. Any other questions? Yeah, maybe I have one question for you, Frank. So on the EBG approach, like how do you see the use of the method with other version of DG? So for example, a hybrid discontinuous Galerkin DG method, or other approaches, and would the results still apply, or do you have recommendations?
Yeah, great question. Yeah, I know there's a lot of HDG work that's been done at MIT. So we have some. It's not in our main branch of the code, but we have written papers on using HDG for shallow water, for example. The reason why I was interested in HDG, I'll just tell it to you this way, was that we were trying to construct efficient implicit solvers, right? That's the idea. And when we started going down that road, I can tell you that since 2009, I've been looking for a sure complement for DG, for standard DG, right, for the Euler equations, right? And we've worked on that for years, and we were able to publish a paper last year showing how to construct a sure complement. So for me, that kind of satisfies that, that requirement, right? That I now have a way of constructing efficient discontinuous Galerkin implicit time integrators, but it's with this idea of linearization, right? Now it's not like that's the silver bullet, right? Because the way we did that is using this, IMEX, what I call RS, RS for reference solution, which means you had to linearize about some state that didn't change. So that, as I said when I started my talk, was not a method that was going to be proved to be stable across all kinds of test cases. So I see that now as a way, as a preconditioner only, right? So it's a great way to start, for example, preconditioning a fully implicit DG solver. So that's how I envision this. But HDG, I'm very interested in it. I really like the idea, but because we're able to find the sure complement, I've kind of moved away from that.
All right, thank you. Any other questions? Yeah, maybe, I'll have one more. So on the time integration part, so as Rodrigo was mentioning, there's the 2 time scale, but then it's also very common already in the ocean to treat the vertical direction implicitly and the horizontal direction implicitly. As you refine, for non-hydrostatic processes, as you refine the horizontal scale, at some point you have processes where mixing in the horizontal, is not that negligible anymore. And so the need for implicit in that direction happens. And so do you have some recommendation on future directions? So either based on the results you have or research of how, like someone mentioned, that's the Russian doll ID, but do you have more precise suggestions or directions that you find promising?
Thank you for that. No, absolutely. Yeah. And that's kind of we have a paper in preparation that essentially uses what I showed today as preconditioners, right? So, the main goal that what we see, so I'll just, I'll let the cat out of the bag, is even for these weather and climate problems, right? Even though you have this separation of scales between the horizontal and vertical, we still see that at the end of the day, what's going to win is solving the full 3D implicit problem. That's going to be the better way of finding a faster solver, which, kind of doesn't make sense when you think about it because of the separation of scales, right? But it is better because especially if you think about it, right? Because when you do the 3D implicit problem and your vertical resolution is much finer than the horizontal, then all of your GM iterations is just solving that vertically implicit problem, right? That's it, right? But then if you use that as your preconditioner, then you now remove that stiffness, and then your GMRS solver is only handling the horizontal, right? And so there you can now increase your time step everywhere. And then you still need a preconditioner for that problem. So that's where geometric multigrid, for example, would come in. And that's what we're doing. We have a geometric multigrid solver that we're working on. It's looking like it's going to work. And we needed a sure complement to be able to do that, right? And we have that now. So I think for me, that's very exciting. It's going to be a way of saying, no matter what kind of problem you give me, we can start with imagine solving a fully implicit 3D problem, and we don't have to worry about stability, right? So now you can argue that there's some things that you don't want to dampen so much, right? Because so you're going to be limited by time stepping depending on process you don't want to step over, right? But it's not like my goal, I hope, is, and that's what I say at the bottom right down here, is that if you have something like entropy stable DG that doesn't break, right? I mean, I can show you examples where I've done 16th degree, 32nd degree polynomials using like solving a solid shock tube problem. It doesn't break, right? So you can do shock waves with it, right? In space, so you have that, and then you have fully implicit time integration time. The code's not going to break. Now, you may not want to push the time step too much because you want to be able to resolve clouds and so forth, but at least that you have that insurance that your code's not going to break if you don't want it to break, right? So for me, I always find it as a way of doing a problem that I've never done before. And if it does, and if my model breaks when I do that, then I know there's something wrong with the problem, right? It's not my solver. And then I can decide, okay, what process do I really want to actually capture, right? So I think that this is the way to go. And I'm not the only one saying that. I mean, there's people pursuing this at DOE labs, for example, are very keen on these fully implicit methods. So I was skeptical because of the cost, but I see a way now forward to bring the cost down. But thank you for that question. Great question.